Good afternoon. Thank you for coming to this talk. The name of the talk is One Move AI Strategy for Alquemists Ascendance. I am Rodrigo Obando. I'm the founder of Ringtuple Inc. I'm just like Joe, he was talking earlier. I'm a one-man band. I'm the one that does the programming, the marketing, the art, the sound, the whatever is needed. With the help of my wife out there, also serve the coffee and breakfast for Simpest. So welcome to coming to this talk, and I want to give you here an outline of this. Is we have the introduction, which we're going to talk briefly about what I'm going to talk about. I want to give a brief, like a few sentences, sort of define what is game AI. What is it that we call game AI? It's not the same as artificial intelligence in general, or anything like deep learning that we hear so much about. Also, we've talked about AI approaches to strategy games, because the Alquemist Ascendance is a strategy game. And then I'm going to talk about how is it that I approach Alquemist Ascendance, and why I took the approach that I did to actually solve the problem of providing an AI opponent, in the game. And then just a very brief conclusion, and have some answers, some questions for that. All right, so this is just my sort of advertising for Alquemist Ascendance. I published a game not long ago. It's a free to play. It doesn't have any in-app purchases or any kind of things. It's a relatively simple game. It's a strategy game. It's based on something that I work on. My day job is as a college professor. I teach computer science, and I do research in complex systems. And what I'm doing, with this game is actually using cellular automata, as the basis for my game. And that's how it all comes from. So I'm going to talk about, what the game is and how it works in a moment. So something I was thinking about, okay, I don't know how many people are actually interested in games or not making games, but I have here says something like games are the result of craftily merging aspects of many a discipline. This is one of the things that have always attracted me about games, is that you could actually join all kinds of things together. In my case, and I tell this to sometimes that I have the opportunity with my students. When I was in high school, which was not like last year, as you can imagine, I was in many, many things. I was from arts. I was a writer, a singer, a dancer. I used to play in the band. Uh, did all kinds of things. I was also an artist. I would draw and all these things. And I also liked mathematics and chemistry and physics and all these things all combined. When I decided to go to college, I became an engineer, and that's where, in general, my craft took me. And I'm an electronics and electrical engineer, all, through school all the way to a PhD electrical engineer, which it doesn't give you much room for many other things. But I like many other things, even composing music whenever I had the time before. So I found that making games is actually a very nice way to just at least dabble in some of those things that you like to do. So that's why I consider games is just a conglomerate of things that you can do. Also, it's I think the questions and the question and answers that we had briefly before. What are the things you can do? Games may use expertise of programmers, 3D modelers, artists, psychologists, mathematicians, musicians, writers, and of course, game designers. All these things are together here. Now, among the programmers, and this I think Andrew Greenberg touched just briefly on. So among the programmers, there is a type of programmer called the AI programmer. The AI, for artificial intelligence. This programmer is a particular type of programmer that has a tough job, because every single AI that you create for a game is going to be different. It doesn't matter what you're doing, what you're working on. Whatever you write is not something like I can generalize a lot, like we could do with, for instance, if we're going to be able to do something in graphics, there are things that we can do in graphics that will be used in a first-person shooter, or it can be used in many other games with use graphics. So we can generalize many of those things, but AI, in general, you have to go back and look exactly what is it that you're dealing with to create an AI. And the different methods and et cetera that exist. So it's a tough job. Um, Besides that, sometimes they might have me that they don't get respect. And I heard this that the AI should not stop the game for publishing. Well, in my case, it did because a year ago I had the game ready. I could actually play it if I play it with somebody, another human, but I didn't want to have the players having to find somebody else that didn't know how to play the game either. So I wanted to provide some sort of AI. So that's actually stopped me from publishing. I didn't have an AI, and it took me a while to really figure out, how is it that I wanted to do it, etc. So to get the AI programming, and that's what more or less what I'm going to be talking about here. So the game programmer, this programmer AI specializes in providing some type of intelligence to the game, and that's what we call game AI. So it's not just general AI; it's game AI. I know that in general, people in the industry, not the gaming industry, but people in saying education. Oh, wait a minute, I'm a professor too. So people in education will tell you that there is no AI in games, because it's sort of simplistic. But there is AI, and there are all kinds of algorithms that you have to implement in order for you to make that work. Um, so, what is game AI? And this is some of the things that I've gathered, with time, etc. So, artificial intelligence may be considered any intelligence that may exist in a man-made device. I've heard that somewhere. Um, Also, this may be achieved by something as simple as an if statement. If something says, "Ooh, there is light. Let's do this." And it sounds like smart. We now know that for instance, you have the lights outside, and at night, and then suddenly they turn on. They say, "Oh, this looks like intelligent." Why? They suddenly realize there is no light outside, so we need to turn the lights on. That's an if statement. That's a if no light on. That could be considered some sort of AI. It's a very simplistic AI. Then we have while statements, for loops, etc. All those kinds of things. For instance, the enemy in a game may be as simple if the player moves to the right, move the gun in that direction, shoot. Simple. But still, if you are playing the game and you see that, it seems like it is reacting towards you, to you. So there will also be finding, animation selection, even generated, automatically generated environments. Whenever you play games such as, let's see, a game that was mentioned today, Assassin's Creed. You will need to go to some place for a quest or your mission, and then you're indicated where to go. All that is used in pathfinding, which is regular GPS, and that's AI. So we need that. So what is game AI? So it is. How can we define this? And this I read. This is I actually found it an Introduction to Game Development. It's an old book, 2009, edited by Steve Raven. This says game AI is anything that contributes to the perceived intelligence of an entity, regardless of what's under the hood. And it was funny because I tried to remember. So what is it? I had this, and then I put it on the internet, and everybody puts it out. And the interesting thing is that sometimes they don't even attribute it to anybody it is coming from. But I believe it's coming from Steve Raven. So given this definition, we wanted to create, in this case me, wanted to create an artificial opponent for the Alquemists Ascendance game. All right. So I'm going to switch temporarily. I don't think I can switch away from this. I'm going to just real quick. I don't even think that anybody knows how the game looks or plays. So I'm just gonna real quick show it in here, and I'm showing it on the wrong. Um, we'll do free aspect. So as you can see, I do this in Unity. All right. So very, very quickly, I'm going to show you there are two modes, strategy and risk. I'm just going to talk about the strategy. It happens that the AI actually works in risk as well. And these are, oh God, you see, this is what I don't like about this. Thank you for pointing that out. Um, let me see if I need to change my settings. Hold on. All right. Sorry about that. Showing now. Okay, good. So that's how it looks. That's the main menu. We have 3 to 7 rounds. As I say, the strategy is one that we actually see the pieces all in front of you. It says full knowledge. Risk is one that you really don't know what you're going to get, and then you need to place it. But let me just run it here without anything. So basically, you have player one on the bottom, player two on the top. Each one of them has what is called a triple. As you can see, there are 8 triples. They're all possible combinations of 2 colors or 2 metals. In this case, gold and silver. So you have, you see that, and it has the triple looks a lot like, and I don't know whether I can mention that mouse without actually ringing bells down in Florida, right? But it looks like that. But it's, for instance, this is silver, silver, gold, and you can see it's around like this, so it's in a circle. So there are 8 possible ways to combine this. So we have 8 of those. Now, whenever you do a round, you are given 4 of those, and the opponent is given the other 4. And the idea of here is that I will then make the moves so that I form my triples and not the opponent's triples. So I'm going to show that in a moment and say, for instance, I think my best bet is moving this one. So I have it in here. So there are 8 empty positions. And now the opponent, which is this one here, probably the best will be, exactly the opposite in this case. So I'm going to try to do this in here. All right. So when I did this move, so there are 2 silver together because I have 2 silver here, 2 silver here, and I have 2 silvers on this side as well. So this one actually, I know that the way that we go is I'm probably going to play it here. Now this one, the opponent in this case, doesn't have any silvers together. So my move in that case is so that I know that my next move regardless. So of course, this one can also counter the same way, having 2 in there. And now I can do this. Now that gives me 2 points. I have these 3, so I combine them together. Now, another thing that I have here is that I can move this so that sometimes for people, whenever people were playing, they were saying, it makes it so difficult because if it is upside down, I don't see, for instance, this 3 over here, I don't know if it looks like anything that I have down here. Excuse me. So I made it so that you can just move it. So you can, you know, um, if you don't see how that looks, if it's closer to your position, so you can just move it and then see it. So now, of course, the idea will be that I'm going to put the gold on here, which will form this one here. The problem is, no, actually, it will give me two because it also forms this one here, which is this one. It's gold and silver, and but then you have um, gold, silver, silver, which is actually this one here. So in this case, my move is going to provide, in this case, if I'm player two, is going to provide two on one side. And then, so it has two of it here, but I actually got one on this side. So on this one, I'm just going to do the same thing, so real quick. And this is, whenever it gets all silver and all gold, and for each one of those, this is sometimes the way that it may go. So it's something like this. In this case, you're tied. So you go to the next round, etc. So I wanted to show you that so that you see what is it that we are trying to do with this. So as a human, you would try to find the patterns and see where is it that you're going to find, the better moves, so that you'll be creating your own. We'll be creating your own combinations of whatever you have, and you're given different combinations for every round. So if I do this again, now I have different combinations. Now I have to do it again. So this is not something that I can just figure it out for this one. Every time that I do a round, I have different combinations, so I need to work this different. As you can see, for instance, here, because I have all gold, the majority are gold, my move in general might be gold as a strategy to start with. So one of the problems, that you have with this strategy, even though you don't really have a lot of moves. At the beginning, you have, basically everywhere, except that you need to make a decision whether you move gold or silver. But as it continues, then you're restricted to the point where at the end, the last player only has one place. You need to still make a decision of whether you play gold or silver. So whenever we had something like this, this is the strategy. This is all you see. You see everything on it. If we were to put it on risk, then you are given either the gold or the silver. So you're not always given both of them. So I call it risk because now it's like throwing dice. I really don't know what I'm going to get. So your strategy might change a little bit. But the AI actually works for both of them. All right. So let me move back to this. All right. So that's, I know that maybe it was not enough for the whole thing, but let's take a look at the approaches to a strategy game. Some of the things that we can do with this is, normally would require strategy, require analysis of both, the battlefield, and analyze the battlefield, and then have a long-term planning and strategy to see what is it that I'm going to do. Okay, I have my pieces placed in some some places in the battlefield, basically. And what do I do? What is my next move? What do I move so that I'll improve the state of the game on my favor? So chess and checkers, are that kind of game. Wherever you have the moves, and then whenever we're playing, the opponent requires to consider not only opponent's pieces, but your positions and etc. But you also your own positions, and then this is what we call the battlefield analysis. So when you look at the checkers or chess, you take a look at everything. I have two nephews, older nephews. I told them how to play chess when they were 7. Whenever they reached 7, I taught them how to play chess. They eventually became masters. They would beat me in no time. But they really got interested in that. The interesting thing was that both of them played different. One is actually has a static analysis of the battlefield, and the other one has more of a dynamic analysis of the battlefield. So checkers and chess, battlefield analysis. If you ever play checkers or chess, that's what you do. That's what you're doing. And the thing with this is that how do you create an AI that does that? How do you evaluate positions and movement, etc.? So the battlefield analysis by itself is an static consideration of the state of the game. You know, we need to sort of plan and take a look at how do I change the game to my favor? How, in the case of ascendance, how can I then make a move so that I will be better off after that move? That's what mechanic. So one of those ways that, and I actually consider this, is decision trees. Decision trees normally are used. For instance, you're in a certain position, and then you have different choices. So, what happens if I go this way? What happens if I go this other way? What happens if I go left? If I go to the right, etc. And then after you do that, what happens if I do this? What happens if I do that? So that becomes a decision tree. If you play things such as, let me see, what is it that actually, the one that I've been playing lately is Detroit. If anybody has played Detroit, after you do, or even in the middle of one of the levels, you can go and take a look at the decision tree of the things that you've done. Or if somebody else played Until Dawn, I believe, it's all the decision tree. The people, the streamers that actually, I remember the one that actually found out how to save everybody in the game. He actually explored all that until he found out what was the particular path through the decision tree that will actually get you there. And those are decision trees. This is what we use to do these things. So for every state of the game, whatever position you are, they will have a number of moves so that we can choose, when you make a decision. And we at that point may actually know which is the best move. If you're knowledge in checkers, there is a particular move that you start with that I think is called the Old Faithful. There's a particular move, and then it's similar as in chess that you have you even call certain openings and defense, etc. So whenever we do something like this, you need to create this decision tree. If you ever curious, you can create a decision tree of tic-tac-toe. I don't know if you ever, I mean, I know you probably have not done it, but you could do something like that. And it might be long, the decision tree. And then that's when you realize, oh, once I know how to play this, I know exactly what I have to do. And all you have to do is to start this way, et cetera, et cetera. And then you know that the best you can do, if both opponents exactly know how to do, is to tie. So in this case, you have, something that you can explore. What happens with checkers or even worse with chess is that as you develop this and you try to see a path for planning, which one would I do? Which way would I move? What pieces should I move? Sometimes, if you want to include long-term planning, doesn't mean that the first move that you make, has to be the best. It might not be the best at that moment, but it might actually pay off down the road. But for that, you had to do all the planning. But for all that, you had to then really explore the decision tree. And it becomes sometimes memory intensive. And it requires a lot of memory and time for processing. And sometimes, you do all that, you make the decision, and then the opponent makes a move that you were not considering at that time, and then now you have to do it all over again. So this is one of the issues that I had with decision trees. So I was thinking about doing that, and then I thought, well, how large are they? How, because the game that I have there is mobile. I don't want to consume a lot of memory in that. So how much can they grow? They grow rapidly or what? So for instance, in checkers, we start with 7 different moves. Checkers are 7 different moves that you can do. Yep, to start. That's rapidly counted. So for every one that you make, there is also another set of different moves that the opponents can make. And as you can do that, if you do 2 or 3 or 4 deep, now you have really not just a tree, it's a forest. You have all kinds of combinations with that. So it becomes really, really difficult to manage. And sometimes a lot of that, you just have to throw it away because it's not useful, right? So when I considered this, I said, well, the possibilities with this, maybe I could do a decision tree because, we start with 8 and actually it starts constricting. It's not like with chess that's actually starts opening up, to all kinds of possibilities. So the problem with the battlefield in Alchemist Ascendance is that you saw it's a circle. Now, if you're in something like on computer science, you would say, yeah, that's just a circular list. But the problem is that when you consider that, when you put a piece in that circle, even though you have, all that is empty, and then you put one piece, it happens that if you rotate it anywhere, they actually is just the same move. It doesn't change. It's the same thing as if you're in mathematics, which I know at least one person around here should be in mathematics, is the rotations. How do you actually do rotations? And how do you show rotations? With permutations and rotations, etc. You normally find what is called the canonical form of the rotation, so that you always refer to that one. So that if you have a rotation for 3, 4, 5, and then you do it exactly at 3, 4, 5, it happens that it's the same rotation as 4, 5, 3 or 5, 3, 4. It's the same, but then you define the canonical form for that is 3, 4, 5. So I had to deal with that in this case because I had that circle. I will put a piece in there and I move it where it's exactly the same move. So that's okay. And then you could say, and it's in fact, I have a circular queue in there. I mean, a circular list in there, which is maintaining that. The problem is, how do I catalog it? So I created a way of creating a canonical form of that. And then it became that it's actually a moving target because depending on whenever you put pieces, your canonical form changes and then it takes you in a different area. You had to jump into trees. And so it became a little bit more work that I wanted to do. So what I did in this case, in this case, if I have, for instance, 16 possible stars, 2 pieces, 8 positions. There's actually just 2 colors times the empty positions, but in reality, at the end is this position are all of those 2 moves. As I move roll or I move the other one. Why? Because it's rotationally equivalent. Yeah, it doesn't matter what they are. So I had to then, if I wanted to go with decision tree, then deal with this and have it that way. So um, I decided to do not do it that way, and what I didn't want it to do, as I said, is depending on what I make, I will sometimes jump in my decision tree because of the canonical form. Maybe if I have looked a little bit harder and find a more stable canonical form, I would have actually gone it that way. But so I sort of said, I'm going to go this other way. Anyway, every for every round, you have only 4 moves per player. So I said, I'm not going to use all that in there. So I put the rotational equivalent positions on the side, and I said, I'm going to do instead a 1 move. So I'm just going to analyze the field, and I'm going to base the best move at that point. So there is no planning forward.
Can I ask a quick question?
Yeah, sure.
I don't understand. When I do the math, the tree's not that big.
Oh no, it's not. It's not. It was not the size of the tree. It was just the trying to find a stable way of representing the rotations,
Okay,
the canonical form. Yes.
So is it fair to say you weren't looking for a brute force answer that would be always correct?
Not at the time. No.
You didn't care about the brute force path.
No,
Okay.
I was not looking for. I was just looking for something simple that will provide some challenge to a player. That would be a little bit meaningful.
I get it.
Yeah,
So you're not looking for just the best answer for the AI to perform, because this seems to be well within reason. Because it's like 16 times, right? It's not that big for it to know the perfect
no, it's not.
catalog.
Yeah, it's not. What I tell my students is I'm a lazy programmer. If I can write less lines of code, I go will
Right.
take that route.
You didn't want a recursive perfect solution. You wanted actually something that might lose, right?
Oh yes. Remember about. I say remember like if we actually have that as a knowledge, body of knowledge, but we want our AI to be uh, has some flaw in there because if it is somehow perfect, we might never win. So there is a flaw in this.
Right. I was looking. The reason I asked again, it didn't seem to be a hard problem to write the perfect. And again, I wouldn't even call it the brute force.
Right.
It's not that deep. It's 16, 15.
No, it is. Yeah, it's just four moves. It's just really.
I didn't quite get that part yet.
Yeah,
I got the opening two, and then I thought you have 2 times 7, 14, then
right. Yeah, it's not deep, and it's actually
12, all the way down.
it constricts, right? But it constricts as you advance. If you actually unfold it all, there are actually 70 different trees.
Okay.
Yeah, there are 70 different trees. So it's not like we always start because our pieces change, when we start. So there are 70 different starting positions.
Oh, I didn't. So it's not just the gold silver. It opens up to more than that.
Well, because of the triples that we have, you're handed different triples for every round. So that would actually present a different goal for every different one.
But to look at, you have the evaluation method,
Yes.
and you could go down. I thought you could go down every path by 2 times 14, 12, 10, 8, whatever. You could go down and just calculate, and then pick the best strategy from that. But again, that would be perfect. It would never lose unless it had to lose, right?
Right.
So, but I'm sorry.
Yeah. No, I understand, and that's why I actually put it in there. Yeah, there was a consideration for that, but I decided to just do it a simple one move analysis. Yeah.
Which is really cool, actually. I mean, I like that notion.
Yeah. So I could have gone that way, but I decided no, I'm just gonna do.
The reason I'm going to ask something is I thought you were implying that your unwieldiness caused you to make this.
Oh no.
And I didn't see the unwieldiness because I saw that from brute force it seemed to be a fairly straightforward.
Right.
I
Yeah.
understand how that's not in your goal.
Yeah. No. That was, and it was not that. It was also finding the equivalent positions. The position that was probably part of the main reason. And I thought, I think that might be enough. I want the AI to at least the move. It will have some meaning. It has what we call about something like that. I'm trying to call it some measure. Actually, I call it that in my program. Like a norm. You have a metric. And then by following that metric, and then you say you're trying to improve on that metric, a maximization of the metric. So it made it very simple from that point of view. All right, so if I do a one move, I don't have to be thinking about, I find in the equivalent positions or the equivalency of all these. I don't have to be rotating anything. I just do a simple analysis like that and elimination of this. The other problem with the circular, because it doesn't have beginning or end, when you think about representation, I mean, if you have an array, if you have other things, you normally have left to right, etc. But anything that is analyzed in circle, you need to consider that if it is actually rotationally equivalent, it makes it difficult because now you have to move, as I said before, everything to a canonical form so that then you can part from a known point. So eliminated all that, and I put all this thing as the journey of I wanted, an AI. I actually asked students, and I said, if you write me an AI for this game, I'll pay you. It's just consider it an internship. And then nobody wanted to take it on. So maybe next time I'll have some more luck with somebody. So I decided to do it on my own. So what I use is a very simple strategy, and also to illustrate that sometimes you don't really have to do a lot of of work to actually have something decent. So the idea, the idea for this, I use scoring priority queues. So the approach is to try every possible move and give it a score. So I have, a given number of empty positions, and I try each one of the pieces one at a time. I score it given the pieces that I have, and then the score is based on how close, whenever I move that, the board turns to my favor. And, how much of those triples that are, sometimes we'll be missing things, how close are those to my pieces? And there's an analysis that can be done in there. So every possible move and its score is stored in a priority queue. Priority queue is a queue that actually orders the thing by a given priority. In this case, the score is the priority. In that way, so once all the moves are stored in there, all I have to say is give me the next in the queue, which is the one with the highest score for the move. And that one high score is the one that actually give me or give the AI the greatest win, the greatest game in when you do this. So if there is more than one move with the same score, you can actually have, two or three with the same score. What I just do is randomly choose. And that actually makes the AI sometimes thinking, oh, it made a different move. That's because it had the same score, but I randomly chose, a different one. That also allowed me to do, if you look at the game, I have challenge, which is this level, and practice. What practice does is that I don't take the first highest score, but the second. So it's not your best. It doesn't really do the best, but it allows you to practice, makes you feel good that you're winning. And that one's actually very simple to do because what I did is I created what I called bend priority queues, which is not just a straight priority queues, but is a priority queues of lists. And each one of the lists is actually has all with the same score. That's why I call it bin. There are bins for each one of those. And then all I had to do is, if the bin has, more than one, then I just randomly choose one. And whenever I do practice, I just take the second bin, which is not as good, and then that's the one that plays. So let me show you. Sometimes I think about whether to show these kinds of things because let me see, preferences. I think I wanted to change this to um, oh, they changed this. Okay. Um, '20. Yeah. I don't know if it can be seen. Hopefully, yeah, you're not too far away, right? So, um, this is in Unity, and the way that this actually works is that whenever the the AI needs to play. There is a point in here. So this is what I had all my talk ready, and then I said I need to go back and review my code because I haven't looked at my code in a while, so that when I'm here, I don't do exactly what I'm doing, which is finding my code. I think in general, all right. So here, there you go. Find best play. So it's a very simple. It's a very simple process. Here I take a list of all the triples. The triples are actually all the triples in the game, which is 8. So I take each one of the triples, and then I do it depending on the turn. If the player 1 or player 2 is doing the turn, then I simply add the triple. So if it's player 1, I add the triple that actually corresponds to that. So this list at the end is going to have the triples that say if I'm player 1, it's going to have my triples. The triples that are below. Let me show you that. You see the triples below? If I'm playing that, no, these are the triples that that list is going to have. So when I do that, then I put it into a bin. I create a bin priority queue, and that's the one that handles all this. And then I create a Movekeeper. Movekeeper actually has a move of the player, and it just has the information, and then it makes it actually very simple to handle down the road and say, okay, I have a Movekeeper that actually contains makes move in here, and then what this one will do is it takes let's see. Down here, let's say we're player 1. If the comes in here, it says create a new move keeper. Down here, now I don't even see my here. So it creates a move keeper, takes the piece, piece holder takes the piece, and then takes the measure. The measure is how good is this move, and what it's going to do is going to try each one of those. It's going to create a move for every one of those. And then this one will do, we'll go back to here. This is the one that actually makes the measure. Takes the list of triples, takes the piece, and then what it will do is will take each one of this. It actually has um, it is in fact I call scratch circle because this is one that I actually try things and then I can discard and I try things and can discard. And what this one will do is find the worthiness of this move. And it actually has 5 positions that you can see on the top. So when I put that move, how much is that worth? And that's what it will go down in here. And it considers, for instance, if I make the move, will I give points to my opponent? If I give more points to my opponent, then I actually reduce that, and then you see this gain over here, -3. If I actually gain something, it is 3. Depending on how many ones I match in the triple, if it is empty, you're not gaining anything. But if you actually are matching in the triples, with each one of this, then you actually get more of this. So there's a little bit more of intricacy in how to in fact handle this, and I have it commented out in here. So we see on the top it says we check for a complete triple. If it is if it is, we use a special test. Here, if there is a complete triple that is being formed, then I actually account for that. It's a and the if that complete triple didn't give me anything, if the gain was 0, that means that triple is complete and it doesn't belong to me. It belongs to the opponent, -3. That's the penalty. If it's not a complete triple, then it will actually come in here and then it takes a look at each one of these and then it finds how much of gain do I have, how much of matching that particular move gives me in here. And then at the end, what it does, it returns the total So for this one, I call this crash circle is because, as you can see the piece over here, I actually removed the piece because I just put it temporarily, measure the battlefield and see how much do I gain for this, and then remove it. And then I do that for every single position that I have. Then each one of those, and this is the measure, this is the score, this is the old one, this is an old way that I had to do it. Then when I get all those, they're actually placed into the bin priority queue, and this one all it does, it sorts it with different queues, and then it brings it back, and let me see, is it here? I actually always make that move, and then I select if this is AI, then I actually play that move. And the reason what I was saying before, where are you? MK. There you go. So I use this, and this is part of the things that sometimes will get you. If you let the AI play, you will never see the play, right? Because the moment that you move it, immediately the thing actually does all the analysis and plays. You never see the uh, the system actually move or make the move. So what I created is an artificial delay. It's like it's moving the piece, and it's all done with the AI play. So the AI play, all it takes is an MK or a Movekeeper, which is the one that I just found in there. One that I got from the bin priority queue. I said this is the best move. So I just call this one. If anybody knows about Unity, you realize that this is a one that you are actually calling in a different thread, right? You spawn a thread. So I spawn the thread, you for about 1 second, and then I have to say the MK play, and then switch to player. And that actually delays so that I can see it, it's about a second. Because if I don't put that in there, then you will never see, it feels very odd if you're playing with something like that. So when you do this, um, let me do the stop in here. Um, I'm going to put it to play. So you see, at least you have some sense that, oh yeah, somebody is moving. See, it waits, and then it comes back to that. So all that is wrapped in that little thing. So all I have to do is find what is the best move, and then just delay it enough, and then play it. So this was player, it was playing against itself, and it's using the same AI. So um, if you work with risk, let me just quickly show you that. You see, you only have one piece, and it's randomly selected. So sometimes I don't really like playing that way because you end up losing because you didn't have a good set of plays. See, that's the tie, even on the risk. Okay, so so that's how it actually at the end it plays. There are all kinds of things that sometimes I like to do, um, and I explained what I was saying before is that whenever you do something like the AI, uh, you cannot sort of just show something and generalize unless you actually show exactly, okay, this is our battlefield, And I like to do something that is not like checkers. I mean, we could do checkers. For instance, I do this in classroom, in the class. So I can show checkers, and I can show how to move and to do all these things and how to implement the AI for that. Um, but if we move to another game, then you have to think about a completely different way. And you have the generalized ways, like we were talking about binary trees, I mean, decision trees, etc. But the best is to actually show up with an example. And, something like this, you have to really get deep into that. And what I wanted to do, as I said, when I asked for some of my students to actually write an AI, was to actually take it as an opportunity to see how they will actually solve the problem. But nobody actually took up to the challenge of doing it, and I ended up doing it myself, and it works okay. As I said, it's a one move approach using priority queues and scoring, for each one of the moves. And it turned out to be actually simpler than I thought originally. So, so in conclusion, sometimes the simple solution is more powerful than you can imagine, and that's what happened to this. As I said, I was doing what I think it was Joe. Joe was mentioning something this morning in the talk. It's saying, you know, don't think about it. Just do it. And then I was just trying to come up with the best way to do it, and I found out that that way was actually a lot simpler. So once I hit that, it took me like a couple of days to actually write it and do it. And I know that Joe and I would talk about sometimes that we don't want to do something for the code, and we just keep it, and then later on we fix it and say, oh, geez, well, I've done this a lot, you know, earlier would have been actually good. And that's sometimes what I think about something like this. So anyway, if I have any, I will be happy to respond. And I didn't think I was going to take this long, so apologize. Well, we started late, right? All right. No questions? All right. Thank you very much.